In this presentation, this is the second part for the lecture 8. We'll be looking at the Python implementation or some aspects of the Python implementation of the supervision and management and maintenance layer. And this is the script that I'm using here to illustration is actually done for some other purpose. It was done in connection with the more realistic research project. So it involves already a lot of additional behaviors and functions. It's much more realistic in a linguistic sense. So if you download and open the script yourself, you will find that it's much more complex than the other scripts that have been designed to be as simple as possible and usually to illustrate just some one thing. But this is already a much more complex program that is doing linguistically more realistic things. So let's keep that in mind. I will be focusing here on two things, the data management and then the logging. These are the first things that we need to have in the system to work with anything more realistic. And the starting point, let's begin with the data management. What this component has to do is that it has to read the data, it has to understand and read the data as it exists in your data sets. So it has to be able to parse that file, to ignore or process all the comments or all the other type of special symbols we are using. Also, it has to understand how the data is packaged. For example, because we are using an enumerative grammar, the dataset will have numerations paired with the desired or attested expressions that the model should be creating. Here is an example from the dataset that we will be using here. So each data item is a numeration followed by the sentences the model should be derived. And so your supervision layer has to be able to understand this information, how it is packaged here. It also will have to ignore all the comments. And sometimes when the project gets more complicated, I'm using special symbols and notation to modify the simulations. For example, I can pick up just one data element for processing if I want. All of this functionally has to be coded in the supervision layer. Now, when it comes to the data handling, my view, the best approach is simply to define a class, a special class. I think it's called language data in this script that I'm going to show. And this script will handle everything that has to do with data reading, generating output from the data, checking the results of the simulations, and parsing the dataset files. So that all the data handling is in one place, in one class, and in one module. And the module that I have here is called language data. This all is now inside of the same script because this is still quite short script, so it's not divided into separate modules as you would do if the project were more complex. But you can see that I have here defined the class itself. It contains a list which stores the dataset. And this list will be a list of pairs where the first item will be the numeration that it gets from the dataset file as I just showed. And the second member will be a set of output sentences exactly as they were in the dataset. So that's in this particular script the way how the datasets are represented internally. And then we have a function here which is reading or parsing the dataset file. And this also knows where to locate this file and what the name will be. I won't go into it because it's not relevant here. Just to point out that all of this has to be part of the supervision layer. Then we have a logging related function, but I will talk about the logging soon. And then we have another function which is comparing the output from the model with the data in the data sets, or data set in this case. And this will be reporting the output for the user. We will run the script at the end of this presentation. So its own class, perhaps its own module also, where we implement everything that has to do with data manipulation and internal representation of the data. Now let's talk about the logging next. I want to make some general comments first. Python, the standard vanilla Python comes with its own logging functionalities, a logging module that can be used to create detailed logging information, and then the user can easily control the amount of details available. And I have used this functionality in some of my legacy code, and it's still, some of this code still remains. But later I discovered that this Python's logging function was really not very useful for me. It has been created for my view, it has been, the primary use case for that module is to debug complex, very complex commercial systems, systems which have very heavy requirements for usage and optimization. So in the end, I concluded or came to the conclusion that the best way to do logging, at least in my own research, is simply to open the log files before the execution begins, and then simply store the logging information into those files during the execution. And it's important to update this logging information to the files quite frequently, because if your program is crashing, it's usually the log files that we will start to look for the reasons, and then it's important that when the program crashed, that the logging information is quite recent. So we open the file, and then during the execution we send this information into these files. That's the basic idea. Now, the way how I'm doing it in this script is that when I'm executing grammatical operations, things like merge, or there is also movement operations in this script already, this logging information is collected first into a kind of a global string variable. This is, in this script, is a class variable, not the object variable, but forget about that. We have a global storage, a string, where we can add string information as the derivation progresses. And then quite frequently, this contents of this variable is emptied into the logging file. And then it's resetted to 0, and then there is another. We rewrite it again. So now I just show what I mean. So let's begin from the derivational search function. So it's here. This is quite similar to the function we already looked. But here is an additional piece of code or function called consume resource, which is writing into the log file the contents of the old working memory, the contents of the new working memory after some operation has been applied, and then this variable here, the logging report, is the string where I collect information of the operations as they are performed. I will show again a concrete example. So this is a little bit more complex script. So I had to look for where I find a good example of this happening. Here, for example. This is phrasal A movement. Let's forget about what it is. It's a grammatical operation that the theory assumes is part of the human language faculty. And here you can see, after I've decided that this operation should be executed, we are simply adding information to the logging report, to the class variable, that we applied this operation. And we also adding information about the objects to which the operation was applied. But you can have anything here you like. It's also possible that you write this information directly into the log file here. But in this case, I manipulate the strings and then only periodically send it to the log file. So exactly when do we send it? Well, in this case, I will send it quite frequently. As you saw here in the derivational search function, every time we are applying some operation, I'm going to go and write it into the file. Now, why is it like this? Well, the reason is technical, and it has to do with the fact that some of these operations are always, or not always, but are applied in a sequence. So they are actually, what is one operation from the point of view of derivational search function is actually a sequence of smaller operations. So I will gather that sequence first into this logging report before I will write it into the log file. That's simply the reason why I'm adopting this system here. But you can see that the logging is part of the derivational search, and it's continuously monitoring what the system is doing. And so now I will just show you what it looks like, the output of this type of logging. So here we are deriving the item 2 I just showed. That was the numeration. This will be written into the logging file first. And then it also takes note of the predicted outcome. This came from the dataset. And then it just begins. Here it prints the contents of the syntactic working memory. The first step, we have these 5 elements. And then it triggers the merge. So this information is added to the logging report when this operation itself is done. And we print out the contents of the working memory after the operation. Remember, this was exactly what we coded in the consume research function. I show it again. So here it is. Print the contents of the working memory, print the logging report, and add the contents of the new working memory. Now, just to make a brief comment, but this was already came up in the previous presentation somewhere. These print commands are implemented in the corresponding classes. So if I'm printing, when I'm printing this logging report, this is simple string we print as such. And here we have print constituent list. It's a special function in the script that will print us these lists as you saw them here. So this list is another function which is doing this, is exhausting the contents of the syntactic working memory. So then we, after the merge, we have this situation, and that's then the input to the next call. And then we merge the dog. We get the complex noun phrase, the man dog. It doesn't make sense, but as I pointed out, we have to explore everything. And so on, everything is recorded. And we see how the derivation itself progresses. some small detail here. You can see that this algorithm is already printing the labels for complex constituents. So there is a separate function which calculates this label. These are so-called pair phrase structure representations that don't have complex labels. The labels are calculated on the basis of what they contain. And so there is a separate function that provides this information, and then it's added to the function which prints phrase structures in the bracket notation. And so you can see that this is really crucial information when you start debugging or understanding what your grammatical theory is actually doing. Here you can see that we reached the one final phrase structure, and it was also accepted. So the acceptance is created by the post-syntactic function which verifies that some independent grammatical constraints are satisfied, such as lexical selection. In this case, it verifies that the byte, which is transitive verb, has adequate direct object, the man. Now, where do we have this selection for the verb? They are now defined in the lexicon here. So this script has already more complex, of course it's not that realistic, but more complex lexicon where we have each lexical element is mapped to a list of a set of features, and the model is then has functions which interpret this information. Those pieces of code know what these features mean. So that's one way to implement the data handling and the logging. Quite simple in my view, but it involves a lot of coding because of a lot of the details that is involved. Now, I just want to look at finally the function which calculates the correctness of the model, and then I will just run this script to show what it is doing. And actually, I will also have to remember now, I want to show you also the executive code which runs one study. What is that doing? Well, let's put that aside and look at this evaluation first. But the function is here, evaluate experiment. It's called after we run the model with some numeration. And we get output from the simulation. This is a set of expressions, strings created by the model. We have gold standard data set. This is the set of expressions that we expect the model or predict, or the set of expressions in observed reality we have in our data set, gold standard data set. And then it's simply, so these are sets of expressions which are strings. And then we simply checked if we have sentences in the output that are not in the dataset. And this will be stored, these expressions will be stored into a set of overgeneralization. This is a set of strings as well, meaning that our model created some output that was not in the dataset. It predicts that some expression is attested or real that is not in reality, so has not been attested. And then we do vice versa. We take we check if there are expressions in the gold standard dataset that our model was not creating. That's undergeneralization. So our model fails to predict the existence of some pattern that is observed in the real world. This minus symbol here is simply taking removing from the set of output from simulation that set every sentence in the gold standard data set. And so the residuum is what represents overgeneralization. And errors is simply we add the size of both sets, how many overgeneralizations, undergeneralizations there were, that's the number of errors. And that's what we print out to the console. And here I'm also reporting that if we have some errors, it reports simply the sentences that were generated but should not have been generated, and sentences that are missing. So that's the simple function that does the comparison. So let's quickly run the script. I will show first what I have here in dataset more broadly. So you can see that we are testing with simple transitive sentences, intransitive sentences. This T star here is my way of telling that I'm using some kind of artificial or ad hoc element in this simulation. I was simply illustrating something. The T refers to tense. So I was probably discussing the notion of tensed verb. That's what this numeration is about. Then we added tense. This small v is transitivity. So I'm adding transitivity as a grammatical notion to the examples here. Then I'm adding the force. It's represented as C usually in the grammatical theory, aux inversion, and so on. So this already has a lot of linguistically, I would say, more interesting things. Here is some data, very long calculations tagged out where numeration has 1, 2, 3, 4, 5, 6, 7, 8 items. So this is so complex and takes so much time that I have simply commented it out so that I can run this rest of the script in a more smooth way. So if you want to see a really long computations, you can remove this comment from here. But that's what we have in the data set. And then I can try to, the last thing I'm going to try to do here is to run this. Let's see what happens. Yeah, I let it run there. It's going to now deriving these sentences there in the background. As you can see, it is printing out the sentence as a linear sequence of list and then the phrase structure. The sentence is created by the linearization algorithm. You can also see that sometimes it stops, it does nothing, and then it continues. And this is because it goes recursively all the possible ways of applying the operations. I think there were 3 basic operations already here, and then some of them were composite operations, so they do several more primitive steps. So when it stops processing, it means that it's exploring some branch in the derivational search space which is not able to produce anything linguistically meaningful. If the algorithm makes a wrong operation in the beginning, it applies, for example, the and the verb, then everything else that happens after that steps, all this huge amount of exploration will never lead into anything. And that's why the processing kind of halts for a while. Now, of course, you want to, if you know beforehand that the and verb can never be combined, then you can filter out that solution by having the preconditions. So defining the preconditions. So you can say that don't combine the and verb because the never takes verb as a right sister, for example. But still, even if we do that, and in this script I have done I've added the preconditions and they are relatively realistic already. You can't block all dead-end exploration. This is because there are some combinations of words which in the context of this numeration will never produce anything useful, but then you can't block it completely because in some other context it can and might produce a grammatical output. So I'm just letting it run in the background now, although there is not much interesting to see. Again, there is some long dead-end branch that is exploring. Well, when it's doing, let's do something else. I thought that I want to explain what the actual model is doing, the executive part. So I move to look at that briefly. As I told you in the previous presentation, all these function definitions that I give here in the beginning of the script, they are just definitions and they don't do anything before I call them explicitly. So here at the end of the script, I have the I have the lines that are really executed when I run the script, as I just did. So what happens here is that we create this language data object first, which will hold the data from the data set. And then we have then that object will read the data set, and the name for the data set is provided here, so that I can run this with the different data sets if I want. And then we create a speaker model, and the speaker model is now a notion that I will return later. It has to do with the fact that different group of speakers, Italian speakers and Finnish speakers and English speakers and so on, we can't use the exact same model to predict their behavior. So the speaker model is something that captures that aspect, and it's already part of this script because this is more advanced, but we can put it aside because I haven't explained what it is yet. And then we trigger the run study function, which takes the data and the speaker model as input. And the speaker model, that I wanted to say, we have to know that the derivational search function is part of the speaker model in this script. So that's why it is an input for the run study function. And the run study function is here. It initializes the logging, some variables that had to do with errors and the data set. And then it goes through every numeration and gold standard sentences from the data set in the study data sets that is provided in the language data object. Because as you saw from the script that it was running, it takes every item from the data set and derives each one of them and then moves the next. And this is the loop that does this. Remember that the study dataset variable was just a list of pairs where the first item is the numeration and the second is the set of expressions we want this model to derive. And so that's here, the numeration and the gold standard dataset are the two items from this pairs, from the list of pairs. And here we are writing information to the log file. So it will always stamp, it will always create a data, raw output data, but what is it that we are, I actually showed it already in the log file where you saw that the numeration was printed out and the data set that we are supposed to generate. That was printed there in the log file and that's done here. And then we will send the numeration into the speaker model. It has the function derive, which it then calls the derivational search function. So here I'm activating the derivation. And finally, we go to evaluate the output. The total errors will count the total errors after we run the whole experiment with all the data sets. I call it somewhere batch testing, meaning that in one script we test several data items, several numerations. So that's it. And now I think that the script has already finished. Let's go to verify that. Yes, here it is finally. And you can see that there are some errors left, again, because this was not supposed to be a research itself, but it was used for some more complex. This was done in a connection with the study where I wanted to estimate the amount of calculations that we need in a somewhat realistic grammar. So this is all, and all of this processing created the log file. So every step of all of the things we did is in this log file. And you can see here, this is the end of this log file. That it's quite a massive file. It's 9 million lines of text and almost 300 megabytes. So we are talking about a massive amount of raw output data. So this has all the steps that were executed when I derived all those data items from the dataset I just showed. So that was a brief description of on the implementation of the supervision, management and maintenance layer. There are much more here involved when you go into more advanced models, but these are the basic elements. So to summarize briefly, all the data processing is handled inside of its own class and module, and that will store the data and read it from the files and compare the output of the model with the data we have in the datasets. And so when it's reading the dataset, it has to also know how the data is structured there. So it has to be able to parse that information. And in this way, all the data processing is separated from the empirical part and also from the executive layer.